something here. All right, we've talked a lot about how to deal with gravity. We know when we have weight in a problem, we're going to substitute mg. We've talked quite a bit now about friction. That if we have a problem that has friction, depending on how friction is being used, we may be dealing with static friction or kinetic friction. And although we're still working some of those out, those are problems where if friction is involved, we're expecting them to tell us something about or ask about the coefficient of friction. I'm having trouble with my drawing thing. I don't think it's catching up. I mean, I've drawn something on my screen, but it's not there. See, there it is. The radius of curvature simply means that our bit of a circle has a constant radius. It is a circular path, but cars don't generally drive in a circle. They drive in portion of a circle and then the road straightens out again. You know what I'm saying? So we describe the portion of the drive where the object's road is curved as having a radius of curvature. That phrase you're going to hear a lot. Now this is a weird kind of acceleration. It's an acceleration in which the object's speed isn't changing, so we can't compare the final speed with the initial speed and divide by the time. The speed is going to be staying constant. So this kind of acceleration we call a centripetal acceleration. And it's a big word, but you'll probably see where it comes from in just a minute. A centripetal acceleration. To make it distinct from a regular acceleration, I will always write A with a little c next to it to remind myself that we're dealing with a centripetal acceleration. And a centripetal acceleration is calculated as how fast you're going squared divided by the radius of curvature. Now, this is the kind of thing that you guys generally don't get into your notes, and so I'd like to have you get this down. When it comes to traveling in a circular path, this tells you how much acceleration is required to make that turn. Meaning, if you want to, say, make a left onto Citrus Park Boulevard from Sheldon, you guys know the place I'm talking about? It's not an easy turn to make because it's more than 90 degrees, so a lot of people screw it up. When you hit that turn, the velocity and the radius are going to be fixed based on how fast you're going when you enter the turn, which means that there's going to be a certain amount of acceleration that your car is going to have to experience in order to make the turn. And it's a combination of how tight do you want to make that turn and how fast do you want to be going. Is it clear to you that if you want to travel fast, your turn radius is going to be a problem? Because obviously if you go fast, the velocity is squared. And if you're going faster than the acceleration your car tires can give you, you might have to make your radius bigger because it's in the denominator. You guys see that? So it takes more acceleration to make a tighter turn. Being as R gets smaller, if you look at your picture here, if R was to get smaller, that would mean your turn would get tighter. Right, that's a smaller turn. That would be a smaller radius of curvature. That would take more acceleration. And obviously, if you want to go faster, that's going to take more acceleration. So when it comes to turning, the acceleration behaves a little different. But also, there's something else about this that I want to be very, very, very clear about. This acceleration doesn't change how fast you're going. So when we look top down on the car, this acceleration has to be perpendicular to the velocity, because it can't have any component in the direction of motion. So as a car turns, its velocity changes direction. but doesn't change size. That means the acceleration also has to change direction, because the car's acceleration is always going to be perpendicular to the velocity. The car's acceleration is always going to be perpendicular to the velocity. Now look, there's a lot of fancy geometry here. Like all the velocities are tangent to the curve, and all of the accelerations are perpendicular to the tangents. Those are complicated sentences. So I just want to tell you what I want you to know. The centripetal acceleration always points towards the center. That's what you need to know. The centripetal acceleration always points towards the center. It's in the name. Centripetal means center pointing. So when we say centripetal acceleration, we are saying that the acceleration points towards the center. Okay? Everybody good so far? Now, here's where I need to make you understand something. There are no centripetal forces. So you might hear that phrasing, centripetal force, and it's technically incorrect. There's no new force here. Our list of forces hasn't changed. What is different is that you can have an unbalanced force that doesn't change how fast something's going. You can have an unbalanced force that changes what direction you're going. Again, you can have an unbalanced force that doesn't change how fast you're going. You can have an unbalanced force that changes what direction you're going. For example, this car that's making a turn here, how many forces do you think it's experiencing? Can you name one? Gravity would be one. It's hard for me to draw gravity in this picture, isn't it? Because we're looking at the top of the car. I think you guys would expect that if I drew the car, like over here, and draw the car to the side here. So here's the tires. There's the, I don't know, the back of the car, the bumper. There's, I don't know, is that a car yet? Is that a car? Or just a stack of cake? I don't know. We'll say it's a car. If that's the car, and here's our license plate, because there's a car. And we're looking at the back of the car. Is that okay? So you would probably agree that there is a downward force due to gravity. So we could draw a downwards arrow and say gravity's acting on the car. What else is acting on the car? There's got to be a normal force acting on the car. So I'd probably draw a force like that. Normal force acting on the car. But something has to be acting sideways on the car, right? Something has to push the car to the side, because that's what's causing it to turn. What force is left that we haven't used? Oh, the silence of second period. You have a list. Think of it. Is there any cables causing the car to turn? So I don't think it's tension. And do you think it's the buoyant force? I mean, you have a list. It's going to have to be one. Is there a spring connected to the car that's causing it to turn? All right. Anybody have any idea? Interesting. You've all driven a car and have no idea what makes it turn. Yeah?
Would the friction be?
I think that's the only thing that could possibly be doing it. I want you to imagine if there was no friction, do you think your car would turn? I mean, if you're driving like on icy roads, right? You see them all the time. They can't turn. They just go straight. It's friction. You turn the wheels in such a way as the friction pushes against the car. So in the case of the car making this turn, friction is the unbalanced force. You turn the tires to generate friction and direct it towards the center of curvature. I know you don't think that's what you're doing, but that's how you get your car to turn. is by using friction and directing it. In this case, it's got to be static friction because the tires don't slide with respect to the road. In fact, since it is static friction, and static friction has a maximum, the amount of unbalanced force you can get to make your turn is limited by the static friction. If you try and exceed it, your car will slide. It happens all the time. If you look at the corner of Citrus Park and Sheldon, you'll see all these black smudges on the far curb when people didn't make the turn and hit the curb. Probably because they tried to go a little too fast and their car broke traction. So what I want you to understand is for anything that moves in a circle, there will have to be an unbalanced force to cause it to change direction. It's going to be from your list of forces. It's going to be friction or tension or normal or something. And it's that force that must be unbalanced to cause the object to travel in the circle. Mm-hmm.
So why wouldn't it be kinetic friction?
Because the tires aren't sliding with respect to the road. When they come down, they stay in contact and don't slip with respect to the road. Does that make sense? Mm-hmm. In fact, you're trying to make sure that happens, that you stay in contact. I want you to imagine this, because I think some of you may have experienced this before. And this is kind of what roller coasters do too. Have you ever been in a roadway where there's been a dip in the road? Like so. Or a roadway where there's been a dip in the road in the other direction, like. So say this is your car, and you go down into this dip, and then you go over the top of this hill. Okay, can you imagine doing that? You ever notice that when you're at the top of the hill, you feel kind of light when you go over the top of the hill? When you go into the dip, you feel kind of heavy at the bottom of the dip? Well, this can help explain why. In the case of the dip, let's look at that first. There's a radius of curvature here. The radius of curvature is like measured here. Because the road is making a dip, the circular part's underneath it. And on the other side, the radius curvature is the other way. Does that make sense to you guys? You see what I'm saying is a radius of curvature? When you're at the bottom of the dip, what two forces are acting on the car? It only has to be two.
Gravity, normal force.
So gravity for sure. And because it's in contact with the road, normal force for sure. Now here's where you guys won't write something down, but you probably should. Those can't be balanced. Because if they're balanced, then the car travels in a straight line. And is the car going to travel in a straight line? Nope, not if it wants to stay on the road. Therefore, it has to be unbalanced towards the center of curvature. The only way that happens is if the normal force is greater than the weight. It's the only way that happens. So when you go in the bottom of a dip like that, your net force is unbalanced because you're traveling in a circular path. And on this circumstance, the normal force will be greater than the weight. That's what's causing it to be unbalanced. You feel heavier because the road pushes up more on you while you go through this turn. You don't think of it as a turn, but it's a circular path. At the same time, if you go to the top of it, if you're at the top of a dip in the road like that, not a dip in the road, a hill in the road, the weight of the car can't be any different. So the weight of the car is the same. It doesn't change. But now the force has to be unbalanced downwards. Because of that, the normal force has got to be less. So you feel lighter at the top of the hill, and you feel heavier at the bottom of the hill. In fact, roller coasters play with this all the time. If we look at the one on the right, in that case, the weight is greater than the normal force. And remember what I said, always make your positive direction the direction of your acceleration. So I'm going to make the positive direction downwards because it has to have an unbalanced force downwards in order to be accelerating downwards. So in this case, this is the positive direction, the direction of the weight. So weight minus normal force equals MAC. Now what you feel is normal force. You don't feel your weight, you feel the response of other things to your weight, like the pressure of the seat pushing onto your butt. That's how you feel your weight. So in both of these, on the left side, your normal force is going to be greater, right? Because you're going faster and faster through that dip, so we can make you feel several times your weight if you go fast enough. This is why if you've ever been on a roller coaster at the bottom of that first hill, when you're going fast and the roller coaster just came off the hill and turns real quick, haven't you ever felt like you're really being pressed down into your chair? That's why. Your inertia wants you to go this way, but the car is lifting up. You have to increase that upwards force to do so. But we also can do the reverse. Let's solve the one on the right for normal force. When I solve the one on the right for normal force, I get weight minus MAC. Is it clear the normal force is going to get smaller? The faster you go, the smaller it can get until it reaches zero. When it reaches zero, you're no longer in contact with the chair. Did we ever ride Gwazi back when it was a real wooden roller coaster? That is what Gwazi used to do. It used to have a couple of inverted hills where you felt like you were going to be thrown out of your chair. That was on purpose. They did that so that you would feel as though you had no normal force and you'd come off of your chair. It was the way it was designed to make you feel like you were being thrown out of the ride. Either way, in both of these circumstances, to solve these problems, you'll have to make a substitution. You'll have to substitute in something that represents the centripetal acceleration. Now, in Citrus Park Mall, there's these. It's in the middle, it's big, it's ugly. It's 2 stories tall. It's a carousel. It's got the horses and the camels. You ever ridden this thing? Probably when you were little, maybe when you weren't so little, right? It's not a particularly exciting ride, is it? And if you've ever ridden it, it just kind of goes in a circle. But little kids seem to like it anyways. And there's a bigger one, of course, at Busch Gardens, and there's a huge one at Magic Kingdom. And there's lots of versions of these rides, right? Dumbo is a version of this ride. It just goes in a circle. I use the carousel because it's got a big platter, like a big platform. You can walk around on it. So is it true that everybody in here has been on something like this where you've kind of walked around on it till you got to your horse or your seat and sat down on it? The whole platform turns. Which horse is going faster? Horse 1 or horse 2? Do you know? Did that sentence just not make any sense to you? Let's say that you're the parent and you sat your kids on the ride and you didn't want to ride. You wanted to sit over here and take pictures as they go by. Does that make sense? So you put your 2 kids on there, kid 1 and kid 2. Would you agree that both kid 1 and kid 2 make it back to you at the same moment every time they go around? So it's not like kid 1 can make it there first, right? The whole platform, is moving at the same speed, same circular speed. So let's say it takes 4 seconds for it to go around. Both kids will be back in 4 seconds, won't they? It's not like one kid will make it there first. Which kid is in the bigger circle? Kid 1 travels in a bigger circle than kid 2, right? So kid 1's traveling faster than kid 2. Because the circle that kid 1 is on is a bigger circle. But they both come back in the same amount of time. So when we consider kid 1's circle, it's that big. And kid 2's circle is that big. Does that make sense now? Now, this is going to be hard, and you guys aren't paying it the proper amount of attention. So let's be careful here. There's radius 1 and radius 2, correct? So the circle that one kid is on has a circumference of 2 pi radius 1. Right? That's the circle being traveled by kid 1. And kid 2 is traveling in circle 2 pi radius 2. But they both make the turn in the same amount of time. All good so far? I'm saying this to you because if you needed to know how fast the kid was going, you'd probably have to use properties of the circle to do so. If I tell you the kid makes a turn in 4 seconds and tell you how far away they are from the center, I'm giving you information about how fast they're going. And so the other kid 2, is going that fast. I'd assume you would know this because of geometry, but maybe not. And how about this? Who's ever heard the phrase RPM before? What's it stand for? Rotations or revolutions per minute. Yeah, your engine has an RPM gauge. It's how fast the engine is spinning. And rotations per minute. There's also, if there's RPM, there's RPS. What do you think that is? Rotations per second. That's right. If you guys don't know these things, write them down. Your problems are going to talk about rotations per minute and rotations per second. These are known as angular speeds. So we could talk about the angular speed of the carousel. Now here's the big thing that you guys need to kind of get into your head. The carousel has only one angular speed. The whole thing is rotating once every 4 seconds. In fact, its angular speed is 1 rotation every 4 seconds. That's its angular speed. We use a fancy W as the symbol for rotational speed. It's a lowercase symbol called omega, and it means rotational speed. So an object can have 1 rotational speed but parts of the object can have different linear speeds. I've tried to give you a good example about how that's true. Do you guys see how this example plays that out? Let's do a quick little bit of some back of the napkin kind of calculation, okay? Let's say kid 1 is at the edge, and the edge is 5 meters from the center. And kid 2 is on the inner horse, which is 3 meters from the center. Can you figure out how fast each kid is going? Please try. That 2 meters makes a big difference, doesn't it? So can I pick on people, or are you still hitting buttons? Zane, can you give me V1?
7.9
Excellent. Excellent. Bella, can you give me the other one?
No, I'm still working on it.
I can wait. I am patient. But I might switch to somebody else. You guys got it? What is it?
4.7 meters per second.
4.7. Was that too hard to do, guys? Are we okay with that? All right, so let's say it's a kid. Not big, 30 kilograms. What net force must they experience to make this turn? I know you don't think you know how to do this, but I'm going to show you that you do. We said the mass of the kids are 30 kilograms each. And I asked, what net force must they experience to make the turn? So net force is just MA. Now they're just sitting on the horses, but they're traveling in a circle while on the horses. So this is how fast one of the kids is traveling, and this is how fast the other kid is traveling. They're accelerating, but they're experiencing a centripetal acceleration. So the net force for kid 1 will be their mass times v squared over r for their velocity and their radius. And the net force for kid 2 will be their mass, 30, and v squared over r for their velocity and their radius. Not terrible, right? Not yet. So pushing buttons is no big deal to me. You guys know that. But you're going to see that the kid that's on the outside horse has to hold on a lot harder than the kid that's on the middle horse. This is why, of course, if you've ever been on one of these rides, they tell the parents to put the kids on the inside horse. It's easier for the kid to hold on. Right? And it's not a small amount here. There's a big difference. Now, it's probably more exciting to be on the outside horse. And I want to point out a couple things here that perhaps you've never put together because there was no reason to. But if we go to Busch Gardens, one of my favorite rides is Montu. It pulls a lot of what we call G-forces, but it's just acceleration. So when you say G-forces, they're saying that 1 G is an acceleration approximately equal to 9.8 meters per second squared. So if you pull 4 Gs, it's almost 40 meters per second squared. The human body starts to feel uncomfortable around 7 Gs, but most of you probably get excited around 4 Gs. I'm saying that because Montu can pull 7 Gs a couple times, but it never does so like straight ahead or straight behind. It's not the brakes or the gas that does that. Cheetah Hunt does, right? Cheetah Hunt has that propelling system, so you kind of feel that acceleration that changes your speed a lot. Most roller coasters pull Gs by turning fast. That's how most roller coasters do it. So the loops, the spins, the turns, that's where you get the maximum G-forces in almost all roller coasters. It's not straight ahead change in speed. There's only a few roller coasters that do that. And if you've ridden those, they're exciting. So Hagrid's, Velocicoaster, Hulk, Rock and Roller Coaster, even the Slinky Dog Ride, they all do that by having a mag system that propels the cars forward. And you got that straight ahead kind of drag racer kind of acceleration. But most roller coasters, they pull their Gs this way. In fact, if you've never been to the carnival, have you noticed how many carnival rides spin you? This is why. Because the body can't detect velocity. The body can only detect acceleration. So if you want to have an exciting ride, they want to try and produce as much acceleration as possible. How many of you have ever been one of these rides that sticks you to the sides of the ride vehicle? You guys know what I'm talking about? All right, so this is an excellent physics problem. And you can probably imagine why, because it has all the stuff in it. If you're in the ride and you're stuck to the side because the ride is spinning, you've got circular motion, you've got friction, you got all of it. Right here to the side, draw a free body diagram of the forces acting on you if you're stuck to the side while the ride is spinning around. Let's say we capture it just like this, so you're right at the edge. There's not many arrows to draw here. Did you draw a downward arrow yet? That's the easiest one. Get that one in first. And if you're not sliding down the wall, there has to be an upward arrow, right? So if you want to be stuck there, something has to act this way. What keeps you from sliding down the wall? No. It's got to be friction. It's in the name. Prevent one surface from sliding past the other. This has to be static friction. You want to stick to the wall. In fact, looking at that picture, did you draw that the normal force has to be this way? It would have to be. The normal force has to be perpendicular to the surface. And it has to be big enough to produce friction. So let's consider how we would work this problem out. If you want to stick to the wall, is this a first law problem or a second law problem? I know you think first law, but it can't be. You're traveling in a circular path. anytime you're traveling in a circular path, it has to be a second law problem. All right, if we look at this problem from the top, right, you're here, and the ride is spinning. So you're traveling in a circular path. When I start trying to work out the problem, I'm noticing that there's a clear coordinate system I think I'll apply here, right? I mean, it looks like I could line up all of my forces with a coordinate system I put like this. But I need to have a coordinate system that's pointed in the direction of the acceleration. Well, do you see that that normal force is pointed towards the center? Are you guys noticing that? Because there has to be an unbalanced force towards the center in order for you to travel in a circle. So in this particular problem, I'm going to make this the positive x direction. It's towards the center. I'll make this the positive y direction. Now I'm going to say net force in the x direction equals MAC, because I'm traveling in a circular path. And net force in the y direction, well, that'll equal 0. I don't want to slide down the wall. Now this means I need my static frictional force to be equal to the weight. I need that. It's the only way I don't slide down the wall. But at the same time, the normal force has to be equal to m v squared over r. Now you'll notice I haven't changed any of our set of steps. Have you noticed that? The only difference, the only thing that's changed is I have a different way of dealing with acceleration. So we can continue this, and the problem would continue with things like, well, static friction is equal to mu times the normal force. And this is where I would start going down. I'd probably take all of this and put it over here for normal force, and all of this and put it over here for friction. This is where the problem would continue, doing the things we've talked about. Maybe the problem asks, how fast do I have to spin the ride so that I stick to the wall? Or how sticky do my clothes have to be so I can stick to the wall? Right? You can see where the question's going to come in, can't you? The kind of things they're going to need to ask. If I'm building one of these, what's an appropriate radius? You know, stuff like that. These are all the kinds of problems I think you would expect. But based on wanting to be reasonable for time, centripetal motion problems. Let's sum it up. Traveling in a circle. Traveling in a circular path with a constant speed. Things to know. Acceleration must be perpendicular to the velocity. The forces must be unbalanced. The object must accelerate. The velocity can equal the circumference divided by the time. The acceleration is that velocity squared divided by the radius. And always point the positive direction. Towards the center. I'm going to push the homework off a couple days so we can practice some of these circular motion problems, okay? You should have the rest of them done. We'll do some sample questions tomorrow on this.